So your host today, that's me. If you don't know who I am, you've never seen me before, you don't know who I am and what I do. My name's Simon Whiteley. I'm a system safety engineering consultant based in the UK. I work for my company, Whiteley-Safety Engineering and Management Limited. I've worked on system safety across all parts of the engineering and product life cycle in many different industries, predominantly aerospace and defence, including air traffic control, but also defence land, maritime and defence nuclear, with a touch of healthcare and government IT. Now, I'm an active member of a number of special interest groups focused on developing and promoting system safety and STAMP, and that's one of the motivations behind running this webinar. So just to give you a bit of context about who else is on this webinar with you, well, we've had registrations, over 100 people have registered from over 20 countries from across the globe, so right round from the west coast of America, right round the globe to Australia. So good morning, good evening and good night to everybody. And also people from more than 10 different industries. I mean, it's predominantly automotive, aerospace and defence, but there's a good contingent from railways, nuclear, petrochemicals and software. Now, today's agenda. I'm going to give a brief description of the event. If you've had the opportunity to read or look at the 5-page PDF I linked out yesterday, then you know all of this will be familiar. You can actually get access to the PDF here. I've made it available as a handout, so if you click on the button on your screen, you should be able to download the PDF straight away. Then I'll give a brief overview of how I applied the stamp-based process CAST. And then I'm going to go through and do an overview of my results, focusing on the hierarchical control structure, HCS model, and its development, and then the actual analysis results and recommendations. And then at the end, we'll have a questions and answers session. Now, as I said, I want to keep the main presentation part to 45 minutes, but obviously the questions and answers, I want to make it as useful and beneficial and valuable to you as I possibly can. So if you do have some questions, please type them in the box and we can deal with them at the end. I'll keep going as long as you want, so you can ask as many questions as you want, either easy ones or difficult ones, and I'll stay on as long as you want me to go. Okay, so why is this case study important? And why should you pay attention right now? Well, there's three key things to recognise. The first, with regards to runway incursion, is that it is a significant threat to safety, and occurrences of runway incursion are on the increase. Now, you may recall, you may be familiar with what's termed the deadliest aviation accident in history, and that is the Tenerife airport disaster in March 1977. Now, this was a case of runway incursion where two Boeing 747 jumbo jets, you know, the really big passenger jets, collided with each other on the runway, and unfortunately 583 people lost their lives. Now, this is regarded by a lot of aviation commentators as being the aviation industry's equivalent to the 1912 Titanic disaster, where a large passenger ship hit an iceberg. And then there's two other things to recognise. The first is traditional safety assessment methods are ineffective in a number of significant ways, particularly bow tie analysis. Now, I know I might be coming across as a bit controversial there, and I don't intend to go into the detail of why I believe traditional safety assessment methods are ineffective in a number of significant ways. And I can talk about that in the questions and answers at the end. And then the third point to recognise is that the stamp-based safety assessment methods are more powerful, more effective, quicker, cheaper, and more straightforward than a lot of those traditional methods, and I'm hoping you'll get a feel for that today. So why should you pay attention? Well, I'm going to show you the straightforward power of the CAST accident analysis method using a very basic, very straightforward case study. And I'm hoping that that'll spark your thinking as to how this could benefit you in whatever it is that you do, recognising that CAST accident analysis provides a significant advantage, especially in proactive safety management. So, as I said, the CAST accident analysis is focused on supporting accident investigation, but as in this case, there's nothing stopping you using its power to look at past occurrences. You know, perhaps if you've had a few near misses, you could use this approach to get more insight into that. Okay, so what is a runway incursion? So I know the proportion of the people on here are from aerospace and defence, and they probably know what that is, but there is a contingent that don't, so I'm going to explain that. So the International Civil Aviation Organization, they define a runway incursion in their what's called their PANS ATM document 4444, and that stands for Procedures for Air Navigation Services, Air Traffic Management. And they define a runway incursion as being any occurrence at an aerodrome involving the incorrect presence of an aircraft, vehicle or person on the protected area of a surface designated for the landing and takeoff of aircraft. So this particular incident, it occurred at Amsterdam Schiphol in the Netherlands in September 2009, around 8 o'clock local time. The weather conditions were visual meteorological condition with in excess of 10 kilometre visibility. There was no precipitation, no clouds below 2,500 feet, and it was during the phase of operation for two different aircraft. So one aircraft was taxiing on the ground and lining up on the runway, and the other aircraft was approaching the airfield to land. Now, fortunately on this occasion, the outcome was no damage, no injuries or deaths. The aircraft didn't collide. It was effectively a near miss. Now I've highlighted outcome because obviously this is not an accident, it was an incident, a near miss if you want to call it that, and I'll talk about that in a bit more detail later on. Now these are the two aircraft. The one on the left, G Lear, this aircraft was taxiing on the ground and was the aircraft that did the runway incursion, entered the runway when it wasn't cleared to do so. And the aircraft on the right, this PH Sol, this aircraft was the aircraft that was on approach and had to do a go-around manoeuvre. Now the source information. So this is a Dutch Safety Board report, serious incident report, and it's a straightforward 5-page. It's not a full-on accident investigation report, and it's available at those links. It's also available, as I say, as a handout to this webinar if you haven't already got it. So you're welcome to have a look at that. It is just a simple 5-page report. That's one of the reasons why I chose it, because it's quick and easy to read, it's straightforward. But I'm hoping that based on the results that you're going to see in a little while, you'll start to realise how powerful the CAST accident analysis method is, because starting with this single small piece of, single source of information, there is a lot of value that can be extracted from this. Now it has a straightforward conclusion and no recommendations, so I can't compare the recommendations with the one I've made, but I'm hoping you'll see the contrast. Okay, so for those who are not familiar, this is Amsterdam Schiphol Airport. As you can see, it is a big airport. It's a complicated airport with lots of runways, lots of taxiways, and lots of opportunities for runway incursions. Now, the particular runway that we're interested in is runway 22, which is this one. And on the day of the incident, the runway was operating in the direction of landing and takeoff in the direction of the blue arrow. Now, the area that this incident occurred was on the threshold and entrance to runway 22. So the aircraft on the left, G Lear, that I pointed to, it was initially parked at the Kilo 12 position, and it was given clearance to taxi to point Golf Delta, and then it was given a non-standard clearance to carry on to runway 22, and that's how the runway incursion occurred. But I'll talk about that in more detail later on. So how I applied CAST, a brief overview. So before you get into any kind of CAST accident analysis or any kind of stamp-based analysis, you need to review some source information, you need to collect some information, and you need to extract pertinent information that will enable you to identify the accident or unwanted outcomes and the associated hazards, and then also information that will help you develop the hierarchical control structure, the HCS, and also the timeline, the sequence of events. Now, the information you'll need to develop the control structure is information regarding system components. So things like detail with regards to control actions, control algorithms, process or mental models, depending whether it's a technical controller or a human controller, information to do with actuators, sensors, system disturbances, and context. And then, of course, because we're talking about a system with entities and relationships, we need information with regards to interactions between those system components. And then as you go through the cast accident analysis process, you might need to repeat reviewing your information and potentially get extra detail or clarification. Now, before you actually get into the cast accident analysis process itself, first you need to identify the accidents or unwanted outcomes, then the associated hazards, and then finally the high-level safety constraints. Because the high-level safety constraints are the things that the control structure that you're going to develop is intended to enforce. And once you've done those three activities, this is when you get into the actual cast accident analysis process. Excuse me. Right, so first thing you do is define the control process or the physical process. Now this is essentially the part of your system where physical harm can occur or energy is released. Then you develop the timeline or sequence of events, and then you develop the hierarchical control structure model of the system of interest. Now personally, I prefer to develop the timeline first because the activity of going through that can help you identify the components of your control structure and some of the interactions. So it sort of makes sense to do that first. But it's important to recognize and consider that in this case I've used a single low detail source of information, that the control structure model is an abstraction of reality, and on this occasion it's not been validated. You know, in this case I'm the solo analyst, I've done it myself, I've got no subject matter expert support, so it's not been validated. And of course I don't know what I don't know, and there is probably some important information missing. And of course, you know, I'm biased, everybody's biased, so I may have brought some biases to this. So if you were to do this as part of some real world work as opposed to just a case study, of course it would be appropriate to have a few SMEs with experience, knowledge, skills and qualifications related to the system that you're analysing. And of course, validating the model and getting people's agreement that it's an appropriate representation. Okay, once you've built your model and your timeline, then you analyse the control structure model. So for each hierarchical control structure component, you need to identify and examine the following aspects. So you need to identify safety constraints or safety requirements, safety-related responsibilities, safety-related roles, the control and feedback ability of that particular component. You know, what sensors it has, what actuators it has, and whether there was any issues with those. Then you identify control actions and whether any of those were unsafe. Bearing in mind that when the incident occurred, the controller that issued the control action may not have been aware that the control action they issued was unsafe. So there's an element of outside looking in at the control structure and its behaviour, and also being present and looking out. Then you identify and examine process or mental model aspects, interactions amongst the controllers, and then any contextual factors, and that could be a number of different things. Once you've done that, you examine the interactions, coordination and communication amongst the HSS components, and then of course across the hierarchical levels, focusing on those that contributed to the outcome, including timing and sequencing aspects. So this is where it gets a little bit different to the STPA approach, because the STPA approach looks at all possible combinations, whereas the CAST approach looks at the particular scenarios that you have evidence for in terms of the accident scene and the outcome that you've seen. Then you examine dynamics and changes in or to the control structure, including weakening over time. And even then, during an accident sequence, the HCS may suffer damage or detriment anyway. Once you've done that, highlight those aspects that were unsafe, inadequate, flawed, or not enforced, including failures. And I'm highlighting failures there because, as I said earlier on, most of the traditional techniques, they primarily focus on detecting failures and preventing failures. Whereas you'll see from this, there was only really one failure, if you could call it that, but there were lots of unsafe issues across the control structure. And then finally, record questions observations and recommendations. Okay, so the CAST ultimate goal is to establish what was the control structure that existed to enforce those high-level safety constraints, and then identify how and why each level of that control structure allowed or contributed to the inadequate control at that level, and then make recommendations and suggestions. You know, what changes are necessary to the control structure that would enable those high-level safety constraints to be enforced. And also bear in mind that, you know, real-world systems, when you start to analyze them, it may be that the control structure that you've uncovered may not enforce the safety constraints and may need to have some significant changes if it can be changed. Right, so how I apply CAST, this is going to be the results overview. So there is a lot here that I'm going to go through. And if you do have any questions on this, please just stick them in the questions box and I'll see if I can address them, otherwise I'll leave them till the end. So first off, the accident and unwanted outcomes. So on this particular occasion, for this particular incident, there was no collision. It was minor disruption to airport operations, if that. But there was significant potential for death, injury, damage, destruction of property, major disruption to airport operations, other flights, the national air transport system, and beyond. But it's also important to consider aggravating or special circumstances, because obviously this was not a remarkable day by any means. You know, so things like environmental conditions, it wasn't foggy, you know, it wasn't bad weather. The approaching aircraft, you know, if the approaching aircraft had an emergency or performed a hazardous go-around manoeuvre, obviously this occurrence could have worked out quite differently. So now to identify the associated hazards. So for this particular event, there's only really two. And, you know, as I said, I'm not an expert in airport operations, so there may be other hazards that you as an expert may be able to identify and may be relevant to this. And if you do, please put them in the box. I'd like to see them. But for me, there are two main ones. The first, obviously, is runway incursion. So the presence of an aircraft, vehicle or person on the protected area of a surface designated for the landing and takeoff of aircraft when an aircraft is landing or taking off. And then hazard two, conflicting trajectories that lead to a loss of safe separation margin between aircraft, vehicles or people. So this sort of includes the ground domain part of the system, if you like, hazard one. And then hazard two sort of includes the air flight domain part of the system, if you can call it that. Now, of course, there are other potential hazards that are not specifically associated with this event, but are potentially associated with other runway incursion events, such as, in this case, the presence of animals, debris, or other objects on the protected area. Now, it's important to point out that if you think about this hazard, it also, when you're developing the control structure, it prompts you to also think about other aspects, such as airfield perimeter security and control of animals, for example. Now, I suppose it doesn't apply at, you know, Schiphol Airport, but if you're in another airfield area, another country where you don't have that physical control, then presence of animals could be significant. And it's also important to understand that when you think more broadly in terms of what hazards the control structure is intended to control, it also increases the scope of the control structure itself, and then of course the causal analysis that you do. Okay, so the high-level safety constraints. So essentially this is taking the two hazards that we've identified and transposing those into requirements or constraints that the control structure is intended to enforce. So high-level safety constraint 01, the control structure shall prevent the presence of an aircraft, vehicle or person on the protected area when an aircraft is landing or taking off. And then high-level safety constraint 2, the HCS shall prevent trajectories that lead to a loss of safe separation margin between aircraft, vehicles or people. Now, it's important to also consider that you can where appropriate, break these safety constraints up into safety constraints that are more specific or appropriate to the context of individual controllers. Because obviously, and you'll see later on, that the first safety constraint, obviously the whole control structure has to enforce that, but the pilots and the air traffic controllers, they have different ability to enforce those, and so the requirements for each of those, the constraints for each of those, should be appropriately set so that they can be achieved. Okay, the next step, so the timeline. Create the timeline, the sequence of events. So I tend to use, as a bit of a shorthand, a standard SysML UML sequence diagram. It's a bit of a mashup, but essentially across the top I've highlighted the various entities or organizations, controllers that are involved in this particular scenario. I've put the time down the side, and then the interactions, the messages that have gone between those different entities. So the sequence of events then. So the aircraft captain of G-Lear in the left-hand seat, they reported to the Schiphol delivery controller, and the Schiphol delivery controller gave them clearance for their flight to Luton and then permission for them to start their engines. Then a little bit later on, the KLM Jet Centre, which is responsible for the movement of aircraft on the Kilo apron, they gave permission for G-Lear to taxi from Kilo 12 to Golf Delta. Then the aircraft PH-SOL, they were on approach to runway 22 to land. They contacted the runway controller, the tower controller, and that runway controller granted them permission to land on runway 22. Then G-Lear's captain got back in touch with the ground controller and said that they were approaching the Golf Delta point, and the ground controller issued the non-standard phraseology instruction to continue to runway 22, which is what the aircraft captain of G-Lear read back. Now that was the first unsafe control action, and that is the one highlighted by the incident report. Then there was a 20-second delay, and then the ground controller issued a contact runway controller on a different frequency command. Now there's no information in the incident report about why that delay occurred, but it will be interesting to find that out. Okay, so the aircraft captain attempted to contact the runway controller, but was not able to for a number of reasons. They were blocked, or they were waiting to contact the runway controller. And it does mention in the report that the runway controller was talking to other aircraft, but the G-Lear aircraft continued taxiing towards runway 22, and during that period, the ground controller, for whatever reason, it's not clear in the incident report, they saw out the window that G-Lear was very close to the runway, and so that prompted the ground controller to use the ground radar to establish that G-Lear was lining up on runway 22, which was the runway incursion. Now during this time, it's not clear from the incident report what that sequence was, but the G-Lear first officer who was in control of moving the aircraft, they actually witnessed PH-SOL on approach. They had a visual feedback to see the aircraft on approach, and they discussed that amongst themselves on the flight deck, but concluded that PH-SOL on approach must not be a hazard, and so they continued to taxi onto the runway and line up. Now it's not clear from the incident report, what the discussion was and what the justification was for that action, but that is a key piece of information which we'll talk about later on. Then something happens. There's no detail in the report about exactly what happens, but somehow the runway controller becomes aware that there's an issue and issues the emergency go-around instruction to PH-SOL. PH-SOL does the go-around, and the runway controller tells G-Lear to remain stationary, and fortunately an accident is avoided. Now the runway controller said to G-Lear, you've taxied onto the runway without permission, and the G-Lear captain responded, we had permission from the ground controller. So that shows that the G-Lear's mental model, process model, was that they'd had a valid permission to do what they'd done, and so they, as far as they were concerned, they'd done nothing wrong. But just doing this timeline, just doing the sequence of events, this is really just a superficial analysis of what happened and a partial indication as to some of the reasons why the event happened. And this is where STAMP really adds to this and is, provides a lot of value. So now we create the control structure model. We do some system modeling. So as I said before, we start with the control process, the physical process, and that's related to the high-level safety constraint. Then we ask ourselves, what was the control structure that existed to enforce those high-level safety constraints? Now, I use just a silly analogy, really. I like to think of developing the control structure as completing a jigsaw. You know that you're completing a jigsaw, you know that's the activity you're trying to do, and all you're really doing is looking for the pieces and how they interact and fit together and in what order. And then hopefully once you've done it, the picture will emerge. So this is the standard jigsaw piece, if you like. This is what's called a control loop. So you have a controller that's in charge of the control process, and it's in charge of the process through some form of actuators, and it receives information about the control process through some kind of sensors. Now the controller has what's called a control algorithm, which defines how the controller behaves, and then a model of the control process, which represents the state and behavior of the control process, which is updated by sensory feedback. Now, of course, that controller has a hierarchy above it, so it'll have inputs and outputs and control inputs and feedback outputs. And then on this occasion, I've added also another controller just to highlight that depending on the specifics of the subject that you're analysing, there may be circumstances where two controllers are attempting to control the same process, and that can lead to significant issues with coordination and inadequate control, and we'll talk about that a little bit later on. So thinking in terms of jigsaw pieces and control structures, for me it gives a natural path to follow and a structure to work to, and for me that's what makes stamp-based safety assessment so straightforward, because it leads the analyst, it leads the person to uncover what the control structure is, what important jigsaw pieces there are, and how fundamentally how they fit together. It really organises your thinking and understanding. So as an example, on the right-hand side, I've got just a generic control structure for air traffic control. So we've got an aircraft that controls its trajectory or path under the control of an aircrew, which is under the control of an air traffic controller through some form of radio communications frequency. Now those controllers have airline operator type control above them, airport ATC management. We know that there must be some kind of system design, system operations, and potentially emergency response control structure. We logically know they must exist. We know that a governmental control structure, legal and regulatory control structure must exist. So that helps us to sort of look for the jigsaw pieces, the controllers, the information that we need, and how they fit together. One of the sort of cheats I also use is when I'm going through some information, a document or some kind of report, I extract nouns or entities, objects, people, organizations, processes, and I make a list of them. They're my sort of jigsaw pieces, if you like. And then when I come to build the control structure and see how they all fit together, I can then rationalize that and only select the ones that are most appropriate for the topic that I'm looking at. So I don't get too bogged down in detail. And then the next step. So the next step is to analyze the control structure model. So this is the control structure model that I created from that information from the 5-page report. So I'll just give you a few moments to think about that and look at that while I just have a drink. Okay, so this is just a high-level abstract control structure. I have got a more detailed one. If you'd like to see that later on, I can put that on the screen, but I didn't want to frighten you off with too much complexity. So in the bottom center, we've got the aircraft G Lear, and I've represented both the aircraft captain and the first officer on this particular control structure model. And the reason I've done that is because when you do the CAST analysis and look at the interactions between those two controllers, there's some interesting emergent questions that come out with regards to crew resource management, how those crew behaved on the flight deck on that particular day, but also how the information, how the instructions from the ground controller reached the first officer so that they controlled the aircraft in the way that they did. Because between the ground controller and the movement of the aircraft, some process has occurred that's led to that aircraft being moved in a potentially dangerous way. Now, I'm only going to look at these 5 because I don't want to, there's a lot of other controllers I could look at, but I want to focus on the most important ones. So the starting point for your CAST accident analysis is the control process, the physical process, and then moving outwards through the control structure. So in this case, we've got the first officer in charge of the Gilia aircraft. So this is the CAST accident analysis form that I use. It might look familiar, it might not. So these are the 6 columns I highlighted earlier. So on the left-hand side, I've essentially listed the safety constraints, requirements, and safety-related roles and responsibilities that are included or implicitly mentioned in the incident report, but also those that logically must exist, such as the captain and first officer shall cooperate in accordance with crew resource management principles. So that's a standard safety requirement, a standard responsibility. And then also the first officer shall operate head up for a continuous watch during aerodrome surface operations. So that's a standard practice from the Runway Incursion Manual, Doc 8 9870. But what's of particular interest here is the one safety constraint that was not enforced in this case. And that's high-level safety constraint 01. And I've added a suffix 01 as well because this is about the aircrew. So the aircrew shall prevent the presence of an aircraft on the protected area when an aircraft is landing or taking off. Now clearly that didn't happen on the day, so that's a not enforced safety constraint. Now with regards to control and feedback ability, now all of the controllers that I've selected to analyse as part of this case study, they're all humans, human Mark 1s. Now there was no evidence presented in the incident report that their ability to enact control actions or receive feedback information was compromised. So for example, if the co-pilot or the captain of Gilia, had a bad ear or a bad headset, for example. And there's also no evidence presented in the incident report that the controller's ability to enact control actions or receive feedback had failed or was inadequate. So when the first officer was looking out the window and saw the approach of P8 Sol, there was no mention there about whether he had issues with his eyes or whether he wasn't wearing his glasses if he needed glasses, for example. So control actions. So this controller, the first officer, they issued 3 unsafe control actions. So the first officer taxied past Golf Delta with a non-standard phraseology ATC instruction. The first officer continued the taxi towards and onto runway 22 before the captain had made contact with the runway controller. The first officer continued taxi towards and onto runway 22 whilst P8 Sol was on approach to land. So it's important to understand that in the context of this individual in the system, they believed what they were doing was correct. They had permission to do what they were doing. Yes, there was an aircraft on approach, but as you'll see in the next section, they believed that that was the right action to perform. It's just it was, unsafe. So from the process mental model, so ATC instructions are usually safe. So that's a belief. The ATC permission instruction given to taxi towards and line up on runway 22. So they believed that they'd been given permission to do exactly what they were doing. The aircraft in line with and approaching runway 22, so they'd seen that, they'd identified that, and that aircraft was not a threat. Now it's important to recognise that that was reinforced by there being no radio traffic associated with the approaching aircraft, and that the first officer assumed approaching aircraft was landing elsewhere. And as I mentioned earlier on, that was reinforced by the Schiphol airport having a complex runway layout and associated approach paths. And then discussion with the captain reinforced the view that the approaching aircraft was not a threat. Now, I've highlighted 3 recommendations there associated with these aspects, and I can highlight those later on. Now, interactions. So this incident report doesn't have any detailed information with regards to the interactions between the captain and the first officer on the flight deck, or how the ground controller instructions were received and enacted by the first officer. So were the instructions received via the captain and the captain relayed the instruction, or was it that the first officer was listening to the instruction and just enacted it directly? And either of those 2 scenarios, the issues that were at hand and how to resolve them are subtly different. Then there's no information about whether the captain or first officer recognised and discussed the use of non-standard phraseology, or whether there was discussion between them both regarding the aircraft on approach and the potential threat it might pose. So obviously they talked about it, but we don't really know why they decided to do what they did without contacting, in this case, the runway controller. And then some contextual factors. So the aircrew must trust that ATC instructions are safe, but they're also expected to remain vigilant. Now that's important because obviously the aircrew on a flight deck, they cannot know everything else that's going on outside the flight deck. You know, they have to have some level of trust that the instruction that's been provided to them is safe for them to carry out. You know, there has to be a level of trust involved in that. Okay, so now moving on to the aircraft captain. So the aircraft captain, you'll see that column 1 and column 2 is very similar. So column 2 is exactly the same because we're all talking about humans. There was no evidence that they were not able to enact control actions or receive feedback. But in terms of safety constraints, so the same safety constraints apply. Aircrew shall prevent the presence of an aircraft on the protected area when an aircraft is landing or taking off. Clearly that was not enforced. But in terms of captain responsibilities, so the captain shall safely operate and command the aircraft in accordance with mission objectives, the flight plan, operating rules including aircraft operational envelope, regulations, first officer input and ATC instructions. Now the captain and first officer shall also cooperate in accordance with crew resource management principles, and the captain shall manage the radio communications with the air traffic controllers, including changing radio frequencies, which is what, you know, one of the aspects that they needed to do as part of handing over responsibility between the ground controller and the runway controller. So the unsafe control actions in this instance then, so the captain did not make contact with the runway controller before entering runway 22 or whilst an aircraft was in line and approaching runway 22 to land. So it would be one of the recommendations there is, well, why did they make that decision? Why did they not make contact? We know that there was some delay in, you know, the runway controller was talking to other aircraft, and so that was part of it. But what other decision making was going on there? And then the captain did not stop the taxi prior to entering runway 22 with an aircraft on approach and when the contact with the runway controller had not been established. And also the captain did not query the ground controller use of non-standard phraseology or the delay in instruction to contact the runway controller on a different frequency. Now that generates a requirement which is related to this contextual factor over here. So there's no information presented in the report regarding whether the aircrew are required and qualified to use the radio standard phraseology, and also how that might be enforced by the airline operator. You know, so the question is, are the aircrew required to be required and qualified to use the standard phraseology? And if they are, why didn't this particular aircrew query the instruction, you know, a serious instruction from the controller if it wasn't standard phraseology? So there's an avenue of investigation there that reaches into the flight deck crew, their training and competence and behaviour, and then upwards up the control structure into the airline operator or their training academy, for example. Okay, the process, the mental model. So the ATC permission instruction to taxi towards and line up on runway 22 was given on the previous frequency, and that's not strictly the case. And the aircraft PH-SOL was not a threat, which was the same as the first officer. And then at the bottom, no need to stop taxiing onto runway 22 whilst waiting to make contact with the runway controller because permission had already been granted. So this is an important aspect because, as I said earlier on, the GLIA crew behaved the way they did because they believed that they had permission to do exactly that. So as far as they were concerned, they hadn't failed at what they were doing. There was no failure there. And then in the interactions, so I've already said there's not much information about the interactions between the captain, the first officer or the ground controller, but there's also no discussion about why the captain was unable to contact the runway controller immediately and what the implications of that were. So obviously if the airport's busy, the likelihood that we have a repeat of this incident is increased. So moving on, so the PH-SOL aircrew. So you'll notice there that there's no unsafe interactions, unenforced responsibilities or anything like that, because in this particular incident they behaved appropriately and did exactly what was safe at all times. So I'm not going to go into detail about this one. I'm going to move on. So the ground controller. So the ground controller issued, this is where the incident sort of kicked off. So the ground controller issued a continue to runway 22 instruction with a 20-second delay of then giving the contact runway controller command and the radio frequency. So you'll notice there's a lot more on here than the others. So this shows that this controller was critical to this particular incident. Okay, so the high-level safety constraints, I've emphasized this one. This is high-level safety constraint 01, but it's a third instance of it. So this specific one, the ground controller shall prevent the presence of an aircraft, vehicle or person on the protected area when an aircraft is landing or taking off. And clearly that was not enforced. That's what caused the incident. The ground controller is responsible for controlling traffic in the manoeuvring area with the exception of the runways available for takeoff and landing. Okay, well that was not enforced appropriately. ATC shall use standard phraseology. Again, that was not enforced. And the ground controller shall coordinate with the runway controller. Now, I'm going to hazard a guess that that's not been enforced, but there's no information in the incident report to validate that either way. But that obviously is very important, and you wonder why that wasn't looked at in the investigation, or if it was, it wasn't reported. So the control actions then. So the ground controller issued a non-standard phraseology instruction to continue to runway 22 to GLIA. So that was the first unsafe control action. The ground controller's intent was to permit GLIA to taxi beyond Point Golf Delta to the runway 22 holding point, not to continue onto the runway. The ground controller issues the contact Schiphol Tower instruction with a 20-second delay. Well, that was delayed, so that was a potential unsafe control action. The ground controller inadequately handed over responsibility with regards to GLIA to the runway controller. Now this is where it gets interesting. So there's no information presented regarding whether the ground controller recognised that they had issued a non-standard phraseology instruction and then took action to recover, or whether they didn't recognise that they'd done that and so they didn't take any action to recover. And those two different scenarios suggest very different changes to the control structure or recommendations. The ground controller then operated the ground radar to establish GLIA location, but there was no information presented in the report about what action the ground controller took upon establishing GLIA was a threat to runway 22. So we don't know how the runway controller became aware that GLIA was on the runway. We only know that the ground controller established there was a threat and then the go-around issue was commanded. We don't know what happened between these 2 points, and it's really important to find that out. because that would get to the crux of the issue. The process, the mental model. So as far as the ground controller was concerned, G-Lear had arrived at Point Golf Delta. It was intended to be routed to runway 22 holding point, and that G-Lear was taxiing to the runway 22 holding point. Now again, there's no information about whether the controller was aware or not aware of the standard phraseology instruction being issued, or whether, or in terms of the ground controller suspecting and then confirming G-Lear is a threat to runway 22. So there must have been some reason why the ground controller looked out of the window to see what G-Lear was doing. Now it may be standard practice, that's what ground controllers do, they keep a watch out the window, or there may have been something else going on. It'd be interesting to find that out. Now with regards to interactions, and this is where the incident report is very, there's a lot of information I think that should be considered, is with regards to the interactions between the ground controller and the runway controller. So I've got some recommendations there that I'll talk about later. And then contextual factors. So the ATC must trust to an extent that the aircrew will enact instructions as issued but are expected to remain vigilant. And then the ground controller looked outside and saw that G-Lear was very close to the runway, and that this prompted the ground controller to aim the ground radar at the start of runway 22 and identified that G-Lear was lining up. Okay, so finally, the runway controller. So the runway controller issued a stop command to the captain of G-Lear and also a go-around command to the aircrew on P8 Sol. Now there's no information in the report with regards to what happened between the ground controller and the runway controller, and also whether it was the runway controller that became aware that there was an issue independently of whether the ground controller said something to the runway controller, or perhaps whether P8 Sol on approach, whether the aircrew on approach saw that there was an aircraft, told the runway controller, hey look, there's an aircraft on the runway, and then took action. There's no information about that, and that's key. So the runway controller, so there are a number of issues here. So the high-level safety constraint specific to this controller is the runway controller shall prevent the presence of an aircraft, vehicle or person on the protected area when an aircraft is landed or taken off, and clearly that was not enforced. The runway controller is responsible for controlling local traffic departing and landing, with the exception of traffic under the control of the ground controller. Now this highlights issues with responsibilities and coordination. So you'll recall when I was talking about the jigsaw piece, you have a controller in charge of the process and then a second controller in charge of the same process. That miscoordination often leads to safety issues. And the runway controller shall coordinate with the ground controller. So we've established that there must have been something not right there. But it's important to recognise that these boundary region areas in responsibility can significantly provoke the potential for inadequate or uncoordinated control actions near to and across the boundary. And so, in principle, the control structure should be designed to robustly deal with those boundary regions. And clearly in this case, the control structure was not sufficient to deal with that and enforce those safety constraints. Now, some interesting aspects about the runway controller. So, somebody's saying I've gone mute. Can you still hear me? Can everybody still hear me? Do you want to just type in the box and tell me whether you can still hear me? I'm back in. Okay. Right. Yep. All right. Great. Sorry, you're not all asleep then. Brilliant. You're awake. Excellent. That's what I like. Tell me if you're getting bored. Okay. So the runway controller. So the control actions from the runway controller. So the runway controller issued the permission to land runway 22 to P8 Sol. So in principle, that's a safe control action because they wouldn't have issued it if it wasn't safe to do so. But subsequently, that control action could have become unsafe as G-Lear became a threat. So it'd be interesting to understand what the sequence of actions and events were regarding the clearance to land, the status of the threat posed by G-Lear, and how that became knowledge, how they became aware of that, and then how they dealt with it. For me, that's very important. Okay, so where do we get? Right, okay, so the process, the mental model. So first off, the PH-SOL was on approach to runway 22. Runway 22, logically inferred, must have been clear. PH-SOL has permission to land on runway 22, so everything's fine. But then there's no information regarding how the runway controller became aware of the threat posed by GLEA and whether the runway controller was aware of that threat when they gave the permission to land to PH-SOL. And then again, the interactions, there's no information with regards to the interactions between the runway controller and ground controller. And it's fundamentally important to understand that to really make an improvement to the system and prevent this kind of issue happening again. Okay, so we've gone through the controllers, and now I'm going to talk a little bit about the interactions. So I've already talked a lot about the interactions between the ground controller and the runway controller. So there's no information in the report specifically about that, and we can postulate as much as we like. But all I'm really going to say is that interaction and understanding what was going on there is critical to understanding the causal scenarios involved in this incident, but more importantly, how to prevent them in the future. Because at the moment, simply saying the ground controller needs to learn how to use standard phraseology and don't do it again, that's not going to prevent this incident occurring again, because the issue is with the structure of the controllers and how they interact with each other. And if that structure hasn't changed, then this incident will have a repeat, and next time it might be much worse. I'd also like to highlight the radio communications aspect. So you'll notice that all of those controllers, they interact through some form of radio communications equipment. Now, fortunately on this occasion, there was no technical failures, there was no jamming or blocking of the radio frequencies. But if circumstances had been slightly different, in the case of the runway controller issuing the go-around command to the aircrew, because at the moment we don't know whether the aircrew of PH-SOL even knew there was an aircraft on the flight deck. We haven't got that information, and that's one of the recommendations to understand whether they were aware of the threat, whether they planned to take action, and whether they themselves told the runway controller, hey, do you know there's somebody on the runway? So there's a lot of, what I'm trying to highlight is that this view of the structure shows that it's not necessarily that robust for not only controlling runway incursions, but recovering from runway incursions if they occur. Okay, so recommendations, right. There are 31 recommendations that came out of this CAST accident analysis review. So you'll be wondering, well, Simon, how the heck did you generate 31 recommendations from a 5-page report? Now, granted, 80% of these recommendations are about identifying further information, doing some further investigation, establishing some facts. And then those facts would help you to understand the aspects of the control structure and how the controllers interacted, and then what specific changes you can make to either prevent this accident from occurring again, or at least better managing the results of a runway incursion. Now, I've highlighted 3 red ones, and they are very specific about the runway controller, the ground controller. So recommendation 27, establish how the runway controller became aware of the need to issue the go-around instruction to PH-SOL. And it might literally be as simple as the ground controller sits next to the runway controller and literally taps them on the shoulder. And that's brilliant. So that control structure, there's a direct interaction there between the two controllers. However, if, for example, in the future you decide we want an airport with a remote tower, that it might be possible that physical interaction is impossible. And so whilst the safety constraint is still there on that time-critical communication, the way that interaction is physically embodied is different. It has different failure modes. It has different levels of risk associated with it. And the second red one, establish whether the ground controller recognised that a non-standard phraseology instruction had been issued and whether they took recovery action and what the action was. So this is getting to the detail about understanding, well, you know, how close to an accident were we? You know, did the ground controller know they'd made a mistake and attempted to recover it? Or was it a latent error that we wouldn't detect until later on in the sequence? And in that case, you know, the ground controller's contribution to safety is irrelevant, but we'll come back to that. And then finally, establish why the GLEA crew did not see PH-SOL as an immediate threat, why they did not contact and query the runway controller, and why they continued to taxi onto and line up on runway 22. So there are arguments both ways. You know, the GLEA crew were doing what they thought they'd been told to do, and who were they to argue with the controller at a big complex airport? They clearly know what they're doing, so let's not question them. And by the way, the aircraft is on approach in a bit of an odd position. It is a busy airport, it has got complicated runways, so it's probably not landing here, let's not worry about it. So there is some interesting dynamics there, possibly some crew resource management aspects that need to be looked at in that area. Okay, so key findings. So the conclusion of the incident report is a misinterpretation of a clearance from the ground controller resulted in the crew of GLEA taxiing onto runway 22 without permission. Although the crew observed traffic approaching runway 22, they did not take any further action in response to this, even after some consideration. Now, this is just an incident report. It's not a detailed report. It's not a detailed conclusion. There's no recommendation. So please don't misunderstand my criticism. It is not of the report. It is not of the investigation. It's not of the Dutch Safety Board. I'm merely using this as a contrast between starting with a relatively small amount of information and applying CAST to it and getting lots of benefit out of it, out of the CAST method. So as you saw, I analysed 5 controllers and associated interactions. I identified 27 safety constraints. 9 of those were unenforced, and so clearly the control structure is, you know, needs to be reconsidered, redesigned. The 9 unsafe control actions, 6 unsafe process mental models, 5 contextual factors, and then 31 recommendations, which I said most were for further investigation. Now, if you were doing some continued, you know, safety management, proactive safety management, you could review some of your previous incidents with this method and highlight some areas for improvements. So you could learn a lot from this. You know, it's a simple near miss, but we could learn lots from it. So the key findings: interactions between and behaviour of the ground controller, the runway controller, or the GLEA aircrew were not adequately investigated, or they weren't reported, just to be clear. So further investigation is recommended. The HCS is clearly inadequate. The control structure is not resilient to a straightforward human communication and understanding issue, so it's not resilient to that. The HCS needs redesign, otherwise reoccurrence is inevitable, and you could use the STPA process to do that. And I recommend the use of runway stop bar lighting. So these are the 3 recommendations associated with stop bar lighting, and I'll show you the control structure in a second. So first, establish which air traffic controller has responsibility for controlling the runway stop bar lights. Include a review of the reduced visibility procedures, the runway stop bar lights implementation, the actual physical thing, and effectiveness, recognising issues surrounding globally inconsistent requirements for airports and the lighting. Recommend that runway stop bar lights shall be used in all conditions, and recommend that the runway controller shall have ultimate control and authority to change the runway stop bar lights. No one other than the runway controller shall be able to change the runway stop bar lights from the stop state. And this is why, and you might like this, and if you do like this, I want you to give me some feedback. So this is the control structure, and all I've done is added a couple of interactions between the ground controller, the stop bar lights, and the first officer, because obviously that person is looking out the windscreen and they should see the red lights. Now, in the case that the ground controller did not realise that they'd issued an unsafe control action, if they were in control of the stop bar lights, they may well have set them to go to green in a particular scenario. And that means that the first officer would continue onto the runway and a runway incursion would occur. Now, if the stop bar lights were under the control of the runway controller, then even if the ground controller made a mistake or whatever they did, it didn't really make any difference because the stop bar lights are under the control of the runway controller. And the reason I'm showing you these two control structures is to show there is a difference in the hierarchy. There's a difference in how the control actions are passed and received. And so this control structure, this architecture, is not as safe as this architecture, if that makes sense. Okay, final thoughts. We're really near the end now. Okay, so this event occurred on a normal day, clear weather, with no abnormal conditions. What if the weather visibility was poor? What if the ground controller did not see Gelia out the window going onto the taxiway? They would not have known that that dangerous situation existed. What if the go-around instruction was blocked or not enacted? So again, going back to communication, radio communications, the radio communications method of moving these control actions around the system is not necessarily appropriate for real-time safety critical communications. And what about the aircraft on approach if it was subject to an emergency or unexpected circumstances? Or what if they were not able to go around for whatever reason? I mean, the aircraft, I think it was a 777 that piled in at Heathrow with frozen fuel. You know, that's an interesting circumstance. So it's important to ask the question, is the control structure really adequate for normal and abnormal conditions? Because it might well be perfectly fine for normal everyday conditions, but all you need is one slight disturbance or one slight abnormal situation to throw the whole thing into calamity. And what specific changes to the control structure are necessary to enforce those high-level safety constraints under all conditions? You know, and also any near miss or incident reveals that the HCS was inadequate. So if you have a near miss or, you know, something like that, you know that the HCS is inadequate in some shape or form. So you can use it as a, you know, a precursor to doing some more detailed investigation. You know, it wasn't just a one-off day. This was an issue with the control structure. And incidents are a massive learning opportunity, as you've seen, and it's also a cheap learning opportunity. Nobody's dead. We've not destroyed anything and cost billions. So a couple of questions for you before we get into the Q&A. So what near misses have you had that will worry you? That, you know, ooh, that was a bit close. We need to do something about that. You know, what keeps you awake at night? And would the power that CAS provides help? You know, what I've shown you today, I know it's a very, you know, bit of a Mickey Mouse example, and I've made a bit of a meal of it, I suppose. But how do you think that would fit into your proactive safety management? And that's it. You'll be glad to know. Case study end. So this is the opportunity for questions and answers. So you've got the Q&A box on the right-hand side on your screen there. Please ask as many difficult questions as you can. If you've got a particular slide number or something like that, please type it in there and I can zoom in and jump around to it. This is your time now, your opportunity. Okay, so we've got a few questions there. Let's see what I can. Oh, hang on, what have I done? Questions. Right. Thanks for the session. You're most welcome. It's been a genuine pleasure. Okay, so got a lot of people on today. It's great to see you all. Okay, I can hear. Okay, yes. Right, neither capped. Hi Steve, Lily, good to see you. Neither captain or first officer recognised or challenged the non-standard controller clearance. A missing control action, yes. Well, logically it is a missing control action that they did not challenge the control action. But we have to be cautious about bias. And what I mean is they themselves may not have known that it was a non-standard clearance, and because of that would not have had a challenging control action. You would logically say they should do, but again that raises questions about whether the crew on the flight deck had the necessary training and qualifications, whether they were, performing appropriately, or whether they were just, laissez-faire approach on that particular day. So it would be interesting to look at them, look at the flight deck data recorder if it's available, and then also look at the interactions with their airline operator and possibly their training and currency checks. Thanks for that, Steve. Next one. Okay, so if GLEA crew didn't hear P8 Sol's landing clearance and runway 22 was also open, they could have assumed that P8 Sol was cleared to runway 22 and not 24. Oops, meant 24 then 20. Right, okay. Well, okay, so one of the standard mitigations is, and I'll go back to the control structure picture with the radios highlighted. So one of the standard mitigations is that the aircrew will have a watching brief on the radios, because if they can hear somebody talking on the radio, that gives them a mental model, situational awareness of what's going on around them. Now, we do know that there was a 20-second delay before the aircraft captain receiving the radio frequency for the runway controller. So potentially in that 20-second window, the runway controller was talking to P8 Sol and GLEA missed the opportunity because of that delayed control action. Now, it may be also that during the period that they were on the frequency with the runway controller, that the runway controller was dealing with other aircraft and P8 Sol had already been given the clearance. Or it may be something else going on the flight deck that the aircrew just didn't hear it, for example. That is always one of the aspects. And that's why one of the recommendations is to go and investigate or establish what the sequence of these events were in terms of the ground controller sending the instruction to change frequencies to GLEA's captain, and then when the P8 Sol aircraft received the instruction to land, the clearance to land. Okay, so let's have a look. Yes, does a ground controller ever give permission to flight captains to enter a runway? Doesn't the pilot know that only the runway controller gives that permission? Joanna, that is a cracking question. So does a ground controller ever give permission to captains to enter a runway, and doesn't the pilot know that only the runway controller gives the permission? That's a very good question. So there's two aspects to that. The first is that the pilot's mental model may be that they have no idea what the airport air traffic control structure is. They may not even know that there is a different, if they've operated at a small airfield, the role of the ground controller, the runway controller, all of these other things may be performed by one person, and they don't differentiate that control structure. Whereas at a busy airport like this, they will have distinct people doing those distinct roles, but the control structure will be different. In the first instance, there'll be one air traffic controller with lots of interactions doing lots of responsibilities, whereas in this instance, they're separated out. Now, the pilots may have no knowledge of that. They may have assumed, and I'm postulating, they may have assumed that the ground controller did give them clearance to go on the runway, and they didn't realise that it was separated out and that they must get permission from the runway controller. So you're absolutely right. That's a valid point that in terms of the further investigation that I recommended, you'd need to go and find that out, understand, what was the pilot's mental model of that. But also, that raises an important point from a global perspective. You know, is there a safety constraint? And there is, but how is that safety constraint enforced globally that the aircrew must have a mental model of how that particular airport air traffic control structure is implemented? Because even at one airport, I'm aware that the air traffic control structure, you know, the control structure varies from shift to shift, maybe even changes overnight. You know, at night time when there's not that much traffic, perhaps there is only one runway controller and ground controller doing the job. You know, but during busy hours, maybe there's two. You know, and this was a relatively small aircraft, so they may not necessarily be that used to operating in that environment. They may just presume that they've got clearance. But it's a very, very good point, that. Okay, everyone's going crazy with questions now. I hope I can answer them. Right, so where were we? So thanks, Joanna. That's a really good question, very good question. But as I say, when you do the investigation, you can establish what the mental model was of the aircrew. Is that why they carried on without a clearance? Is that why they didn't question, hey, I need clearance from the runway controller? Because it may be that that was the case. And that doesn't mean that they've failed, if you like, you know. Right, okay, so what's the best reference for how to do such an analysis and case studies like you have done here? I'll be honest, there aren't that many in the public domain. The ones I've used to help me learn and practice is obviously Professor Levison's book, Engineering a Safer World. She has a chapter in there all about CAST. She describes the CAST method in 9 steps. I kind of describe it in 3 or 4 to make it a bit easier to get your head around. There is a good example done by a chap called Paul Nelson. Now, Paul is a pilot who did his master's dissertation at Lund University, I think it was. And if you type online CAST accident analysis, let's have a think. What was the accident called? Basically, the accident he analysed as part of his master's dissertation was an aircraft taking off on the wrong runway. And unfortunately, they took off on a short runway, and I think there was only one survivor who was one of the aircrew. And that's one of the better examples that are available. But unfortunately, there aren't that many. I mean, you're welcome to use this one when I make it available, and I'm happy to talk about it and, you know, give you some support if that's what you'd like. Great job, Simon. Points out the necessity for exhaustive research of existing versus required safety constraints. Can't afford to miss one. You're absolutely right, Steve, and thank you for that. Yeah, so just to highlight the point, so I made it earlier on. If you have an incident, if something happens that is not what you wanted, then it indicates, you know, alarm bells should be ringing. There's something wrong with the control structure, and we need to go and look at it. Because if we don't look at it, we might end up having a big accident, you know, in the future. And for me personally, when you have an incident, it's a cheap opportunity to have a look at what's going on, what's going wrong, but what's also going right that's dangerous and potentially sensitive, you know, to disturbances. Okay, Simon, I've enjoyed your example, and I like the ability to examine the detail of the safety system as you demonstrated. But who do you think would employ this tool in a practical aviation organisation, and how much training is needed in STAMP to employ this? Okay, well, let me just wind that back. So thanks, that's a good question, Mark. So who do you think would employ this tool in an aviation organisation? Well, looking at this control, in fact, yeah, so this control structure then, so you can see that there are various organisational entities at play here. On the left-hand side, we've got the airline operator with their aircraft and their crews doing the missions that they do. You've got the airport, ATC management, and their staff of air traffic controllers supported by the airport technical equipment. I would argue that any of those organisations could take advantage of this immediately. So if you work for an airline, or if you work for a regulator or an investigation board or a particular interested party such as a pilot or controller organization. You know, you guys could take this and analyze your own operations and identify issues. You might identify issues that exist across the interfaces between the different groups, but ultimately looking at it from a systems view, as I've done here, as opposed to from your organization only, allows you to get more insight and more value. So I'd argue that anybody and everybody could take advantage of this, but it is a systems theory, systems thinking method. So it is about thinking about the big picture. And obviously, if you're one of these entities, you will have access to detail that I certainly don't have. But obviously, you'll only have what I call an information horizon. So you inside your organization will have lots of detail about the stuff you do, but the information you have about everybody else will be limited. And I suppose this method sort of prompts people to form a group, an analysis group from these different areas to work together, you know, like I said, as the SMEs, not only to validate the model, but also to understand the subtleties of some of these interactions. Because the power of this method is that it finds the subtle issues that you just don't find as part of the other methods, the other traditional methods. And especially because the traditional methods focus on failures. As you saw here, you know, the pilots of GLEA, they didn't fail. They didn't fail going onto the runway. They had genuine reasons to believe what they were doing was the right thing to do. You know, so this is important. These are important aspects. So, and then finally, how much training is needed in STAMP to employ this? Okay, well, this is a bit of a, as with any method, you have to have a go, you have to practice, you have to share ideas, talk to people, and if you do this on your own, like I've done here, it is a tough thing to do because of all the mental gymnastics you have to do. Because you've got to sort of almost visualize yourself in each one of these positions at each of these jigsaw pieces. Think about the inputs and outputs, the control actions, the sensory feedback, the mental model, how they must have, you know, in the context of where these pilots were sat, what must have the world looked like to them, what made sense to them on the flight deck at the time, but also what makes sense with hindsight, you know, and that's a difficult thing to do. So in answer to the question about how much training you need, I think going through Professor Levison's book, having a look at the webinar on YouTube, having a look at some of the other webinars that I've done, looking at some of the papers like the Paul Nelson master's thesis, I think that's a good one because it's about 20-25 pages and you can get a real feel for it. But ultimately it's about practice. And it's two parts practice. One is getting used to building control structures, you know, playing with jigsaws, and that is a bit of a practice in its own right. Because you're thinking differently. You're not thinking about chains of events. You're thinking about structures. You're thinking about relationships. So you need to practice doing modeling, control structure modeling. And then also you need to practice with this method. So as I showed on like this one here, you've got, in this case, 6 columns. And you essentially go through and fill in the columns, identifying specific information from your source information or your experts, but also inferred information. So in the case of some of these safety responsibilities, obviously I've inferred some of these, like, excuse me, let's go back to the pilot one. So, where is it? PH Sol, no, GLEA aircrew. Okay, so in the case of the captain of GLEA, I've inferred that they must have some kind of responsibilities associated with operating and commanding the aircraft. Now, it may be that there's some specific things in there that I've missed that really needs to be in there and considered. And picking up on the, are the air crew required to use standard phraseology from document 4444? Because if they're not required to do that, then that suggests that the ICAO documents are not fit for purpose. Or if they are required, then why didn't the airline or operator feed that information into the pilots? You know, so there are questions there. So in answer to your question about how much training is needed, I would say you only need like a basic stamp introduction to stamp course, and then it's really about practicing with examples, because that's it, practice. In the States, all standard controller pilot terminology is printed by the FAA, no deviation is allowed. Excellent. So if this was an American FAA covered investigation report, it would be interesting to know a bit more about why the pilots didn't behave appropriately. Okay, so feedback. Really like the HCS element of the CAST analysis and how efficient it can be in terms of integrating the various controls. Thanks, Mark. Good observation. Swiss cheese or layers of safety can easily be displayed like the stop bar used in low visibility, but as you demonstrated, the interaction who controls it can affect its effectiveness. This is a feature that the bow tie would not display efficiently as CAST. That's a brilliant observation, that, Mark. Thank you for highlighting that. So let me just go, well, let's have a look. So on this control structure, I haven't modeled the interactions with the stop bar lights. I've just put some arrows with a question mark. And that's because there is not enough information in the source material to tell me how that important mitigation fits into the system. So as Mark has kindly pointed out, if I did a bow tie analysis of this and I was a runway safety manager or whoever, and I've got my bow tie analysis that says, yeah, we've got some stop bar red lights, that might look like it's a valid mitigation, but clearly in this scenario it's not. And in this scenario, the reason for that is because the procedures for using the stop bar red lights stipulated that they should only be used during restricted visibility. And clearly there's a mitigation there that could have benefited a day when the visibility was not restricted. So let me just pick that up what Mark said. So where is it? Yeah, this one. So clearly I've got two diagrams that show a clear picture of why one control structure design solution is better than another one. It's just literally a change in where the arrow is. It's that straightforward. You can't get more simpler than boxes and arrows. So yeah, that's a good one, that, Mark. Thank you. Shem, hi Shem, good to see you. Sometimes there will be only one controller, or the controller will be working several frequency depending on demand. Yes. So I'm hoping that observation, if you have one physical person operating as an air traffic controller performing these multiple roles, then the actual control structure on the day that that's happening is more brittle, less resilient, less robust, and more likely to result in a runway incursion than if it was separated out with appropriate interactions. Now obviously if it's a quiet airport, then that one person has an advantage because they know what's going on, but they quickly get saturated with information. I mean, there are a lot of incidents of runway incursion where the controller literally forgot that there was still somebody on the runway, and that happens, you know, pretty much every week. And that's not because the runway controller is an idiot or, you know, not very well trained and needs more training. It's because that individual is put inside a system, a control structure, which is structured to cause the accident, cause the runway incursion. And that's not their fault. You know, they're just doing their job. The fact that they've been put in that hazardous structure is just circumstance. So just to add a bit more to that. So if you looked at one of those case studies and did the control structure, you'd see how narrow it was, how much interactions there were, and how many potentially unsafe control actions there were. So you'd know that that architecture is risky. If you wanted to redesign that architecture, you could use the STPA method, which allows you to try different control structure architectures and look at the safety benefits and negatives of either of those. Okay, so moving on a bit more. Had to go, but wanted to say thank you, Simon, for an excellent presentation. You're welcome, John. Thank you for turning up. I really appreciate it. Your support, brilliant. Mark. Hi, Mark. Would it be useful to know what the percentage of control mechanism failures over time to know the priority risks? This methodology seems aimed at taking a single event and make it 100% bulletproof. How would we know if the errors and mistakes may more common over a large survey of operations? I'm not sure how to answer that. I think I understand where you're coming from, but I'm not sure. I'd like to ask you a bit more about that, but unfortunately the person's gone. Now, once you've documented the control structure, if you've got a real system with real data about how many times the ground controller makes a mistake, or how many times we've had a runway incursion, or whatever that data is, you could actually overlay that data on these different parts of the control structure and identify which of those parts is causing you the most trouble. And then you can direct your spend on your safety budget, for example. So if there are issues with people not staying on the right frequency, you could maybe look at that with use this as an insight into that aspect. Okay, good stuff. Yeah, I think your ideas about the lights under the control of the runway controller is genius. Okay, well, thanks, Joanna. I really appreciate that. Even at busy airports at slow times, sometimes the duties are combined. However, here I will be most interested also in the cockpit communications between the captain and the first officer. Yeah, you're absolutely right, Shem. I mean, that is a key bit of information that's not included. So, where is it? Not this one. Right, okay, so there's a couple there. So, recommendation 10, investigate the interactions between and the behaviour of the captain and the ground controller with regards to how the ground controller's interactions came to be enacted by the captain, and then whether investigate the interactions between and the behaviour of the captain and the first officer with regards to how the ground controller's instructions came to be enacted. So was there was there some kind of dynamic going on there? Was there something lost in translation? Was there something else going on? So yeah, you're absolutely right. Okay, Jenny, so thank you. I don't see the hierarchy of controls is followed for this. Interaction by the airport, eliminate the interaction. Are separate runways for in and out not possible? This task is reliant on communication, awareness and following standard operating procedure, all low on the hierarchy of safety. Controls are expected to be partially ineffective, hence their position on the hierarchy of safety. Jenny, that is a cracking observation. Absolutely. So, what we've done here is we've made explicit the hierarchical control structure. And once you see it in its boxes and arrows form, you can start to understand how robust some of those mitigations, some of those controls actually are. And one example I gave was radio equipment. Now, at a quiet airport or where it's not very busy, so long as the radio works fine and there's no issues with interference and people standing on the transmitting button, then it should be fine. But when you start to scale up the amount of traffic, the number of communications that need to happen, the length and complexity of the communications, that part of the control structure starts to look a little bit flimsy. And it's, by making the control structure explicit like this, it allows everybody to see whether the control structure is actually robust or not. And then you can start to ask questions about the design of it. Well, is it really appropriate for a complicated, busy airport to be using radio communications with its inherent weaknesses for such a safety critical operation? I mean, if we're really serious about runway incursion, and preventing another Tenerife, then should we really be operating in this way with these technologies? On the railway, you would say no chance. We're going to have a level crossing with some barriers, some light, bells and whistles. Obviously, you've got to think about the practicalities of that. But obviously, when you start looking at it in terms of the control structure, you can start asking those design questions and using design safety guided design to either eliminate or minimize these opportunities for accidents, not just get people more training or make them try harder. I really like that. Okay, so yes, so Roger. Hi Robert. With three-way communication, should not have at least one of the captain and ground controller have picked up on non-standard instruction? That's a very good question. We won't know because the investigation didn't look at that in that detail, but that is one of the recommendations, as I mentioned to Shem's question. You know, really we needed to know that. We needed to understand what the dynamics of that interaction was and whether it was missed or whether it was detected or whether it was, you know, they weren't acting as appropriately as they perhaps should be. But that shows, you know, when your guard's down, maybe, I don't know. Okay, Mark. Hi, Mark. Incident-related question. Recommended practices for aircrew in using the radio equipment, tune ground and tower, transmitting and receiving on ground frequency while in receiving mode for the tower frequency simultaneously. An argument could be crew obstructed themselves from the broadcast knowledge on the tower frequency. Yes, Mark, that's a very good question, but my counter is, and this is an aspect I was looking at before Christmas about runway incursions with vehicles. So sometimes if you're driving an airfield vehicle, you're expected to have the ground controller's frequency communications on the radio, the runway frequency, and also your mission frequency. So if you're doing bird control or something like that. Now, trying to drive a car on a runway, trying to spot whatever they're trying to spot, whilst monitoring 3 different radio channels and, you know, for safety-related information, is just too much for one person. So if you drew the control structure, it would be one controller with lots of feedback into it. And, you know, humans are not superhuman, they're humans, and we should design the system, we should structure the system to recognize that, and trying to overwhelm them and give them too much feedback to deal with is just, well, it's just nonsense. And as I said earlier on, when you draw the control structure, you can see whether, you know, an individual has too much to deal with by all the different feedback that goes into them. Okay, so is it possible to share your list of recommendations? Yes, it is. There are, obviously when you play the replay, you can pause it and read them all. So you can, yes, you can see those, you can have those. I can't say it's a complete list of recommendations, and it would be nice to see what you think, but we'll see about that. How effective do you think CAST would be for malicious accidents in a security incident? Yes, Roger, another brilliant question. Right, okay. So, I'm glad somebody's asked that. That's brilliant. Okay. So this control structure. So we said earlier on that the ground controller issued an unsafe control action, but we don't know whether they knew that they did that and then took action, or whether they were oblivious and just carried on doing whatever they were doing. So we need to investigate that. Now, we know, because the incident occurred, that this control structure was not sufficient to prevent it. Now, if we look at the security aspects, if we had a ground controller that issued the unsafe control action, you know, consciously, then how would we be able to tell the difference between that? And more importantly, how would we have recovered? Because obviously in this incident, you know, we don't know why the control action was issued like that, but we know the result was a runway incursion. So obviously using this method, we can look at both sides of that. We can say, well, is it a conscious thing that was, you know, criminal intent perhaps? Or was it just, you know, one of those things humans do? Now, just going back, just picking up a bit more about security. So you'll notice that the radio equipment, the radio communications, is a critical part to preventing this accident. So if the go-around command had not been sent or received by the aircrew of P8 Sol, then they may well have carried on and landed on top of this aircraft. I mean, we don't know the geometry. We don't know whether PH Sol knew that that aircraft was a threat, because that wasn't investigated, or it wasn't documented, should I say. But if that radio transmission was blocked, whether it was malicious or not, or even potentially somebody got on the radio frequency and started spouting commands in proper standard phraseology, how would we know? How would the ATC management or ATC controllers know that that was malicious and prevent it? Do we have those secure features? So, you know, just to sort of round that up, using this method, it doesn't matter whether we're looking at safety or security or cybersecurity. It allows us to see the functional issues that exist and give us an insight in what we can do to resolve them. So it doesn't matter if it's safety or security. But yes, so that's a really good question. That I like that. Right, so let's have a look. Next one. Hi, Mark, again. Incident-related question. Oh, I talked about that. Shem, the event you are looking for is the stamp analysis of the Lexington, Kentucky Comair 5191 by Paul Nelson. Yes, it is. Thanks, Shem. So those who asked about another good source of cast accidents analysis to have a look at is Paul Nelson's MSc dissertation on the Lexington, Kentucky Comair accident 5191, Comair 5191. If you type that in Google, it's number one on Google. Good answers. Thank you. You're welcome, Mark. Shem again. Hi, Shem. In FAA rules, while they state that they are supposed to be standard, in my experience in worldwide operators, US controllers and pilots are quite sloppy. ICAO PANS Doc 4444 is a requirement in most of the world, yes. Okay. I will disagree with who said that no deviation is allowed, as it is just not true in the US. I raised this very issue at an industry meeting years ago. Some countries are better at standards than others. Germany, for example, is quite good, but even there we see odd things from time to time. Yes, so two points there. It's all right having the ICAO PANS Doc 4444 that says, hey, everybody needs to use standard phraseology. But as you can see on this control structure with the dotted arrows, how does that information find its way through the control structure? You know, because obviously it's got to be picked up by somebody. It's got to be manifested by, in this case, the airport management or the airline operator. But then how does it get down to the frontline operators? And then the next question is, well, if it does get down to the airport, the air crew and the ATC controllers, why is it not enforced? What is the airport ATC management doing about making sure that this phraseology is enforced? You know, and the same goes for the airline or operator. Because ultimately we've identified that these interactions between the crew and the controllers is fundamental to safety. So, you know, and one way of dealing with that is standardizing the phraseology. But if people are still not using standardized phraseology, then we need to look at how we can enforce that. And being controversial, it might be that perhaps voice communications is not the appropriate method of communicating these safety critical control actions. You know, perhaps it literally should be a red or green light on the dashboard, as a silly example. But all I'm saying is when you do the control structure and start to ask these, what are essentially architectural questions, other options for solving the problem can arise, you know. Because it may be that radio comms is just not appropriate anymore for these complex situations, you know. Okay, so moving forward a bit more. So I will do that. Right, okay, so yeah, that's good. Yeah, thank you, Sarah. Shem. Okay, we've got quite a few questions here. Right, that's amazing. Oh, right, okay, so the majority of bow tie development tools available these days allow you to assign responsible owners to controls barriers. You absolutely can identify who owned that control when using the bow tie. That's fine, Mark. When I meant about identifying people who own a particular mitigation, What I mean is in terms of this control structure. So you make explicit who is in control of that barrier, you know, using that language, and what the control actions and unsafe control actions can mean in the context of the wider system. Well, thanks for that, Mark. Okay, so my opinion of the CAST analysis, Mark. Okay, thanks, Mark. Robust and versatile. I can see how it could be adopted to all various industries as it displays a systems point of view. Universe is arguably pretty much a system, and any systems within this system can be modeled with the HCS. Yes, they can, but it would be complicated. My only challenging question is that I can clearly see how CAST is cheap and fast when used by a single soul, but how complex can it get when various safety analysts perform it, and the difficulty that is potentially introduced in integrating all analysis into one. Thank you, Simon, for the webinar. That's great. It's a good question, Mark. Okay, so in terms of practicalities of doing this method, so I did this on my own, solo operation. It was a pain. It was a bit of a mental gymnastics, but that's because, you know, systems thinking is about mental gymnastics and visualization and abstraction. So you have to be quite agile in how you view the world and how you think about it. Now, when you do this analysis as part of a formal operation, like if one of you guys said, I work for an airline, can you come and give us a hand? It will be a case of get the team together, the SMEs who are experienced in these different parts of the control structure, use a particular case study or example, and then start to flesh out the control structure, and then validate that model as an agreed representation, an appropriate representation of reality. Bearing in mind it is a model, and all models are wrong, some are useful, and all of that kind of stuff. So you agree on the model, and once that core model is created, whenever any change is made to the real world, the model also needs to be updated and changed as well. And so long as that model is carefully config controlled, and people who interact with it and the analysis that is based upon it is carefully controlled, then there shouldn't be any issues. But it has to be config controlled and looked after. It can't just be willy-nilly, it has to be carefully managed. It is a good point. And then it's about managing change. So managing system change, managing CAST analysis or STPA analysis change. But obviously, the good thing about this as well is once you've made one of these control structures, if you want to make a change to the system, you can use the control structure as a starting point and do your safety assessment, change assessment, and identify where the issues might arise. And then build the safety requirements into it from day one instead of waiting for a new design and then finding problems with it and then having to live with them because you can't afford to change it. If you've already got the control structure, you can postulate what design solutions you need without spending any money. Thank you, Simon. You're always an inspiration, and I look forward to future webinars. You're most welcome, Joanna. Thanks very much. I really appreciate that. Shem, stop bars are effective for the most part, but it is surprisingly easy to miss them also under certain conditions, perhaps partly because they're still relatively new. So a good point. That would be about mental models of the aircrew and their control algorithms, as well as external disturbances such as weather conditions, aircraft geometry, all that good stuff. I've got to go, but this has been really useful, and I shall take it back to the office and pass on the knowledge to the team. Great, thanks. That's exactly what we want. If stop bars were present at every airport, along with the runway status lights systems such as are in place at Paris and a few other airports around the world, yeah. Well, that's from a control structure perspective. So we're talking about airport ATC management and the layers above that. So let me just jump to another picture of the control structure. So here's one I made earlier, as they say, in Blue Peter. Right, where is it? There, not that one. Right. I'll use a complicated one. Right, so please don't be put off by how complicated this is. There is a lot of information there, and I'm hoping that it makes sense. So let's just have a quick look. Right, so this looks really complicated. It's just because there's a lot of information on there. So these higher level controllers above the airport operation. So we've got airline operator, airport ATC management. I've included local regulator, in this case Netherlands government, and then also the pilot airline local regulator, the licensor. So I don't know any information about them, so they're highlighted in purple with some question marks on the interactions. Now, from an ICAO perspective, if there is a standard airport equipment fit, that says your airport shall have these things fitted, one of those standard fit things might be, as Shem pointed out, stop bars and the runway status lights. Now, if you're an airport management and you have not implemented those mitigations, then you might be forced to do it, or it might be optional, and you might be, well, what's our risk budget? Do we want to spend money on that? If you draw the control structure with and without, that will show you what the potential causes of an accident would be and how much benefit getting those things fitted would provide. And I would argue that if the ICAO are not mandating a standard equipment fit across airports, then airport management should be taking the lead, because it's only a matter of time before their airport suffers a runway incursion, and potentially a serious one. So those issues with mandating requirements for airport equipment would be in the higher level of the control structure. So if I'd have had time and more information, I could have perhaps gone up the control structure and examined why the airport ATC management did not, on this occasion, have the airport stoplights installed or whatever it is. So this method allows you to look at those high-level, higher hierarchical level issues. Okay, so can I see the more detailed model view of the model controllers? I'm hoping this is sufficient. I haven't got one any more detailed than this. This is just, well, in fact, I'll talk a little bit about this. So these sort of shaded areas at the bottom, and these grey arrows between the KLM Jet Center, ground controller and runway controller, they're just to represent the physical hard standing running areas for the aircraft. So in the case of KLM Jet Center, they are notionally in control of the ground movements on Kilo Apron and the parking position K12, which is where G Lear was at the start of the incident. Then as G Lear taxied, they moved from the Kilo Apron onto the taxiway, and so they became under the notional control of the ground controller. And then, as I said earlier on about boundaries between responsibilities and loss or uncoordination between controllers, when G Lear went from taxiway to runway 22, there was an implicit change in the control structure between the ground controller and the runway controller. But the actual control was via radio and wasn't enforced properly. And that's what caused the runway incursion, if you want a single root cause. Anyway, okay, so it will be more expected. The other issue that jumped out at me is the first officer was very experienced. An inexperienced first officer can lead to increased workload for the captain and thus easy to miss things. That's absolutely brilliant. Yes, it is. Right. So if you looked at the specifics of the two controllers, the control algorithm, as I mentioned, that defines how the controller behaves. And so if you have somebody who's relatively inexperienced and their controls algorithm is not that mature, then the workload between them interacting with the aircraft captain means that the aircraft captain has to take on some of those implied control responsibilities and then feed back to the first officer the appropriate control actions. So that's a very important but subtle aspect that can come out of this type of analysis with this level of detail. Okay, so Jenny, thank you. You're welcome, Jenny. Most appreciated. Floris, Simon, thank you for this webinar. I found it very interesting. Well, that's good. Well, I hope so. Thanks for your time and effort. You're most appreciated. It's been a lot of time, a lot of effort. Shem, newer systems are coming in for controller pilot data communication that will aid this in the future. We are using it at quite a few airports, and it has been in place for quite some time for remote regions. Yes, that controller pilot data link communication technology, the text messaging aspects, I haven't included that in here because it wasn't part of the case study, but if you included that, what you've done is diversified the communication channels, but you've also introduced some new and potentially dangerous situations, either with control algorithms, mental models, interactions, or the unsafe control actions. So provided, not provided, wrong order, late, early, too long, too short. So there are some quite insidious issues with that, which could contribute to safety-related outcomes. Feedback in the control system is still not adequate. Pilots are supposed to read back all clearances, but they do not always do it, and sometimes even with the readback, the error in understanding is not caught. Yes, that's absolutely right. Now, the reason that is because of the control algorithm and mental model of the ground controller and the aircraft captain. Now, the ground controller says something which is not the same as their intention, and the person who hears that command, they may be expecting to hear something and hear the expectation, not what they actually received. And because the both of those people are in that state, that that miscommunication will be missed. Now, there are, I don't know, in terms of an architectural perspective, there may be technical solutions to that. There may be a simple solution, might be somebody else sat on the outside listening to what's going on as a watchkeeper. And I know that previously, and I was talking about Tenerife, so on the aircraft of old, they usually had a flight engineer, so you had a pilot and a co-pilot and a flight engineer. And those three controllers on the flight deck, because the flight engineer was not involved in the direct flight operations of the aircraft, they were almost a free safety feature, because they could listen to what was going on and what was going on around them and almost have an independent view, a mental model of what was happening. And they could spot things such as that were going on and then put a control action into the pilot and co-pilot to prevent a dangerous situation developing. Now that organisation of three is a very interesting aspect of control structures, and I think that I'll talk a lot about that when I do finish off the Tenerife incident examination. Okay, so feedback in the control system, we talked about that. Right, the issue you are talking about with incorrect communication has happened in the past, and there are regions where pilots are notified to be aware of it. South Korea and Asia come to mind. Yes. Okay, so we're near the end of the questions now, everybody. Does anybody else have any other questions before I crack these last couple? Maria, thank you for the presentation. You're most welcome. Mark, thanks. You're most welcome. Hi, thanks for the webinar. I think the intentional insecurity should differ from unintentional commands. When it is intentional, it could be by using guidelines, following procedures, but with intention of causing harm. So I really don't understand when we say regardless of safety or security issue. Right, sorry, Nazar, maybe I wasn't that clear. So with the stamp-based approach, when you create the control structure, and particularly when you do STPA, so you're examining the control structure, you're looking at all possible circumstances and potential outcomes. Now, how those outcomes come about, whether it's a malicious intent or an unintended intent, doesn't really matter. You identify what are the unsafe control actions, and then you know what you need to do. You either have to do something about them and mitigate them, whether they're intentional or unintentional, or you have to architect your system to deal with those issues. So that's dealing with the control actions. Now, if you look at the causes of the control actions, the causal scenarios, some of those scenarios will be safety related, some will be security related, malicious, and then you look at, well, how do we prevent those? How do we engineer safety guided design? How do we prevent those? And that's where, you know, it doesn't really matter whether it's intentional or unintentional. It's actually how you control those aspects, how you mitigate those, that makes the difference. I don't know if that's very clear. It is getting quite long now. Thank you for the webinar, Yuri. You're most welcome. Many thanks for the presentation. Well presented and very interesting. Well, I hope so. I hope so. You're most welcome, Mark. Tassos, thanks for the excellent presentation. You're welcome. Good to see you on the webinar. NASA, thanks. You're most welcome. Okay, so I think that's all the questions. If there's anybody still here that would like to ask anything else, please ask now. Otherwise, I'm going to call it an evening because I've been going on for nearly 2 hours. Okay, well, I think we'll call that an evening. Thank you very much for attending. It's really appreciated. I hope that's been of value. If you do have any other questions or comments, please just get in touch. If you would like some help, I am available. You know, send me an email. I'll set up a meeting. We can have a chat. If you need me to get on a plane in the middle of the night because you're worried about something, just give me a shout. It will be a genuine pleasure. So thank you very much. Have a good night. Have a good weekend, and we'll see you on the next webinar. Thanks a lot. Bye-bye.